Let's get started. Welcome everyone to the April meeting of the Science Engineering Council. It's here every second Wednesday of the month, and we're looking forward to today's good discussion. I don't think we have any new members to announce, is that right? But thanks everyone for their contributions and the memberships. I'm sorry, was there anybody else who wanted to comment on the members?
You have a new member, Bill? I just made today. Oh, good for you.
Okay. All right. Again, thanks everyone for being here and your contributions and memberships.
Wait a minute. Somebody do have a new member.
Oh, we do.
Karen Appledorn.
Karen Appledorn.
Karen Appledorn. Thank you for mentioning that, and welcome, Karen, if you're here. Appreciate that. Let's see. Just want to mention, we say here on our flyer that the Science Fair Awards recognize top winners. We've been doing that for many years, and as many of you may know, Science Fair has kind of been on hiatus, but it appears that they're coming back. Is that fair to say, Yvonne, that we think by this time next year?
2025.
Yeah. So we look forward to seeing the Science Fair version 2 as they come back, and we'll continue to contribute to them. And then other scholarship foundations as well. Okay, so with that, I think I'll go ahead and turn it over to you, Yvonne, to talk about our upcoming meetings and introduce today's speaker, please.
Okay, great. Thank you, Tim. Let's see. I just wanted to let people know that subtitles are available in the Zoom session if you turn on show captions, and you can type questions into the Zoom chat during the talk or ask them after the talk. And let you know that recordings of many of our past meetings are also available on our YouTube chat. Just to give people a heads up about some upcoming talks we have quite a few scheduled. I've got the next 5 topics to announce. On May 8th, Dr. Prajakta Kulkarni will be speaking on AI for disease prediction and early detection, opportunities and challenges. And we have the information for that, and we'll be sending it out fairly shortly in email. On June 12th, Dr. David Ballantyne from UCSB will be speaking about DDT and nuclear waste pollution off the Channel Islands. On July 10th, Cassandra Phillips from Bruker company in town will be speaking on their nano IR technology. On August 14th, Dr. Susanna Scott, also from UCSB, will be speaking about plastic waste. We're having a number of talks about plastic. On October 9th, Dr. Allison Santoro will be speaking about engineering biodegradable plastics for tomorrow's ocean. As always, feel free to contact me about particular topics or speakers you'd like to suggest for upcoming meetings. And as far as events held by other groups around town, we're listing those in our emails now. And so you can check the emails with us for times and links. Just in the next week, we have April 11th, the Las Cumbres Observatory is having astronomy on tap. Their topic is the fastest stars in the galaxy. On April 12th, the Ocean Conservancy is having a meeting on plastic-free future, a vision for California's coastal resources. On April 12th, the Santa Barbara Astronomical Unit has a talk on the race to find life in the universe. And on April 18th, the KITP has a public talk on recent advances in understanding quantum spacetime. So lots of things going on around town. Speaker today is Dr. Stephen Trainoff. He's a scientific fellow at Waters Corporation. Dr. Trainoff develops analytical instruments for Waters Corporation, which acquired Wyatt Technology last year. These instruments are used to characterize macromolecules by measuring static light scattering, dynamic light scattering, differential viscosity, and refractive index. They can be used to measure molar mass, molecular size, diffusion constants, aggregation state, and conformation. Instrumentation by Dr. Trainoff developed is in active use in 8 Nobel Prize winners' labs. His PhD is in physics from UCSB, which is back then is when I met him. He's speaking to us today on why do chemical and pharmaceutical companies care why the sky is blue. And he's just returned late last night from watching the total solar eclipse. So Dr. well, welcome Dr. Trainoff, and thanks for being here today.
Thank you very much for having me. Yeah, let me give you a little background about me. Born in Los Angeles and went to Caltech as an undergraduate in physics. And then I came to UC Santa Barbara and got my PhD, and that's where I move on and correct. And one of my biggest tricks is I was able to find a job in town and stay here. So I've been with Wyatt Technology for about 27 years. And like I said, it was recently acquired last year by Waters. When I joined it, it was Phil Wyatt, his two sons, and maybe I think we had about 22 people. And we grew the company to around 200. And then, like I said, last year was acquired by Waters. It's been a very turbulent time. I'm going to talk a little bit about what we do. Okay, so a little bit about Wyatt and Waters, and then a little bit about the history of light scattering. Now, Phil Wyatt would like to say that the company was a light scattering company because that's the first instruments that we developed. But we do a lot more than light scattering. And so it's sort of in our DNA, but I'll talk about a little bit about the theory of light scattering, and then eventually get some applications of how you can use it to do useful problems. Okay, so a little bit about scattering, history, science, a little bit about fractionation, and then some applications. Okay, it was founded in 1983. Phil Wyatt, there's Phil with his panoply of instruments. We have a wide range of instruments. I'm not going to talk about all of them, but I'll briefly touch on a few. Static light scattering, differential refraction, dynamic light scattering, viscometry, mobility detection, and particle fractionation. This is an interesting technique. And they're used in conjunction with each other to solve problems. So I'm just going to go through a little bit. And we acquired 2023. First thing I want to point out is that scattering is really everywhere. It's not just something that happens inside an instrument. It's something that how we perceive the world. So the blue skies, the white clouds, the red sunsets, these are all scattering. Bill Wyatt used to like to interview every candidate by asking them, do you know why the sky is blue? And because in fact, the blue of the blue sky is very much the same thing that we use for analyzing molecular solutions. That's in the limit of what's called weak scattering. The light comes from the sun. It's got an mixture of red, yellow, green, orange, all the different colors, blue. It scatters once and gets redirected toward your eye. And Lord Rayleigh showed about 130 years ago that this phenomenon was why the sky was blue. Now, when Phil asks our candidates and people this question, he's got some really interesting answers over the year. Maybe it's a reflection of the blue. Sure, the ocean is blue. Very blue. That's great. But what about in Kansas? The ocean. Or maybe it's scattering off of water or dust. And that's certainly happens. You know, the clouds are scattering off of water, but in the desert or in Antarctica, where it's very dry, the sky is still blue. It's usually white. Okay, so it's really comes from scattering off the gas in the atmosphere. This is molecular scattering. And like most things, it was named after the second person who discovered it. So the first person to discover this phenomenon was this fellow named Tyndall. And he did experiments of scattering off of smoke and small particles. And he discovered that smoke looks blue. And light on it has this blue cast to it. And so he is basically credited for discovering that blue scatters a lot more than red does. And so again, coming back to why is the sky blue, you got this admixture of light that comes from the sun. They're all scattering. The blue scatters more efficiently. So what ends up is biased toward the blue. There's still red, there's green, there's yellow in the sky, but you end up with more blue. Lord Rayleigh put this on a scientific background, which is why he gets his name on it. And he discovered that in fact it goes to the fourth power of the wavelength. So red light has twice the wavelength of blue. It scatters, blue scatters 16 times more efficiently. And that's why you end up with these blues. But they both were confused about whether it was off of dust or off of gas. And Lord Rayleigh in 1899 published a paper. He said, you can scatter off of molecules. And he proposed this idea of molecular scattering. but he couldn't get the ratios right. Is it particles, is it gas? And to that, this guy came in. Einstein actually solved this problem. And it wasn't in his original miracle year in 1905, but he published a paper in 1911 that basically solved this problem by doing what's called fluctuation theory. The idea is that consider the gas as a continuous medium, and it's got an average refractive index, and there's little density fluctuations due to Brownian motion, and these density fluctuations are what cause the scattering. And so is it particles or is it gas? In fact, it's both, but in a clear sky where there's no particles and no dust, you get scattering in what you would normally consider continuous media, because continuous media isn't truly continuous. Got these density fluctuations. Could I just pause where we're?
Yeah, sorry.
No, yours.
There we go.
Okay. Anyways, but Einstein solved this problem of continuous media. Assume that there's if there's Brownian motion, there's little density fluctuations. There's regions of high density, there's regions of low density. Light comes through and it scatters off these fluctuations. And from this, he was able to accurately predict how bright the sky would be relative to particle scattering. And that's why credit Einstein is the first one to really point out that you get scattering in what we can think of as continuous media, because it isn't truly continuous. Okay, so that's what it looks like in nature. This is what it looks like in our instruments. Our light source is a laser. We have a scattering sample, and then the light comes out of the laser and it goes through the sample. And the things that we look at are mostly transparent. So we're looking at molecular solutions, small molecules in transparent liquids. So 99.9999% of light goes through unscattered. But a small fraction of it will interact and get redirected toward our detector, and we're going to measure it at an angle theta. And so this is what I've described as the static scattering measurement. We're just going to look at the average intensity. How bright is the scattering? And the trick, of course, is making it so you can pick up very weak signal on top of all the other parasitic signals, like fingerprints or imperfections in the glass or other things that can cause scattering. So in other words, to measure the good stuff and reject the bad things. And this is what the inside of one of our instruments looks like. There's a laser and a bunch of optics, and then there's a flow cell or a sample cell inside here, an array of detectors in a ring around it. Okay. So I said we do all of these different types of light scattering. Scattering is a huge field. There are many ways of looking at scattering. We're doing this type we call static scattering, when you look at just the average intensity, or basically what your eye would see. And I'm going to motivate why this measures the weight of molecules and how big they are. So if you think about this, this is a remarkable thing. You can weigh things just by shining light on them, and you can figure out how much the molecules inside them weigh. You can also figure out how big they are. You get this parameter called the radius of gyration, which is an unfortunate historical name. That sounds like it has something to do with rotation. It really has nothing to do with it. It's a measure of the distribution of mass within molecules. So a better name is maybe the root mean squared radius. There's another type of light scattering, which we also do, and I'm going to touch on this briefly, called dynamic light scattering. So if I have a fast detector and I look at the signal, I find that it's not a constant. With static scattering, I measure the average intensity. With dynamic light scattering, I measure the fluctuations. How much is the signal fluctuating around? And from that, you can get a measure of diffusion. And from that, you can get a different measure of the size called the hydrodynamic radius. And then the last one I'm going to talk about just very briefly is electrophoretic light scattering. If you have molecules that are charged and you put current through the sample, they feel the electric field and they move, and they pick up a Doppler shift. And we can measure that Doppler shift with a scattering measurement, and you can measure how fast they're moving. And from that, back out a parameter called the zeta potential, which is related with the charge. Basically, how electrically charged are these things? So you can get weight, you get two different measures of size, and you can get charge. And maybe you can see why pharmaceutical companies might be interested in this. I'm going to try to make that more concrete. Okay, so let's talk about scattering. Where does it come from? Okay, so we see visible light between red and blue. And it is a fluctuating electric and magnetic field. And you can take a very simple model, just assume there are charges within a molecule. Light comes in, the electric field is pointing up, it drives some of these charges up and other ones down. And then when the field reverses, they switch. So you get this dipole of charges point up, and then point down, and then point up. And whenever you have a fluctuating electric field, it acts like an antenna or a source. So if you ignore why these charges are moving and just focus on the charges themselves, so like it's a source that radiates. And so that is the scattering signal that we measure. And it has to do with how much the molecule gets polarized when electric field comes through. Okay, so let's see how this actually measures mass or weight. So if I have two different particles, so here's particle 1, here's particle 2, and they're just diffusing around by themselves. Well, imagine this one scatters a certain amount of light, called I naught, and then this scatters the same amount, because it's the same molecule. It also gets I naught. Now, because light is a wave, you get interference effects. So if you do the math, you find that the scatter from these two things depends on how the waves from this one interfere with the waves from that one. And if it happens to be like when you go out to the harbor, you see the waves come in from the ocean, they hit the breakwater, and they move out, with the crest of one wave going out meets the crest of the incoming wave coming in, you get a wave with twice the amplitude. Where the incoming wave hits a trough of the outgoing wave, they cancel. So light does the same thing. So you can either get twice the electric field or 0, depending on their relative arrangement. And so mathematically, we measure what's called the intensity, which is proportional to the square. And you can get either 4 times the scattering from this one or 0, depending on that relative change. But if you time average, those cross terms go away. They average to 0. So 2 molecules, I get twice the intensity. It's not surprising. I put more stuff in solution, it scatters more. So I've made a concentration detector. That's great. It doesn't measure how much they weigh, though. Lots of things measure concentration. I can measure how much they might absorb at a specific wavelength of light. I can measure how much the refractive index changes. So light is the scatter is proportional to concentration. You put more stuff in, you get more scattering. Now here's the magic. Let's say I wave a wand and I make these things just bind together in what's called a dimer. Now what happens is when the light comes in, it scatters off this one. Since it's tied to this one, they're now in sync. The light comes in synchronized from the laser, but now I always get constructive interference. So the electric field from this is twice the electric field from each one of these. And so the intensity is always 4 times. So just by not changing the amount of stuff I put in solution, just making them rearrange themselves to be something that's either heavier, where each molecule is heavier, the dimer is twice the weight, then the scattering doubles. And so if I measure the concentration to figure out the effect on the right, and I measure the scattering to get the effect on the left, I can extract the mass. So just mathematically, the scattering is proportional to the mass times the concentration in appropriate limits. So if I measure concentration, I measure scattering, I can measure mass. So that's a remarkable thing. You shine light on it, and if you know how much each one scatters, you can figure out how much they weigh. Okay, so where does the size come from? Okay, let's say I take a big molecule. So this is one that the polymer chemists love. They call it a bead on a string. So this molecule has one mass element here, another one there, another one there. They're all connected together. So what happens when this scatters? So before, I was talking about is they're really small. So when the light comes in, they drive the two together. But if they're big, like I put a marble and ask, how does light scatter off a marble? Well, the front half of the marble and the back half of the marble are so big that they're not necessarily small compared to the wavelength of light. And so I have to ask, how does the light that scatters from each individual part add up? But this one is a particularly easy one if I look at just what happens if the light were to go straight through. So the light can come in, go to the first mass element, and be collected. Comes from the laser to the second mass element, be collected. You notice these distances are exactly equal. If I'm a little bit closer to, if I'm a little further from the laser, I'm a little closer to the detector. If I'm a little closer to the laser, I'm a little further detector. So if they start out in sync because it's a laser, they'll end up in sync. So at 0, always constructed. The interesting thing is you go to a finite angle, the distance traveled from here to the mass element of the detector is not the same as compared to this mass element of the detector. So the idea is if they started out in sync, they're going to get out of sync. So you get some cancellation. Now this sounds very mathematical. But what it means is that you start seeing a decay in the intensity. So here's the scattering from 0 to 1 as a function of angle, 0 meaning right here, and 180 meaning backscatter, and decays. I guarantee you everyone in the room has seen this, even if you didn't appreciate what was happening. Next time you go to the movie theater, and you look at the screen, see a beautiful image. You look back at the projector and you realize you see all the dust particles sparkling in the sky, in the air. That's this effect. That backscattered is suppressed compared to forward scattering. And so when you look at the detector, at the projector, you're doing forward scattering. If you look at the screen, you're doing backward scattering. This is, I showed here, the change for a molecule that's only 20 nanometers. Okay, it's only a 5% effect. When you have things like dust, where they're 10 micron or 20 microns or whatever, this effect, instead of being a 5%, it may be 10,000 to 1. So next time you go, homework to everyone here, measure the size of the particles in the beam by figuring out how much is forward scattering and how much is back. Okay, but the key point is, if you measure the angular asymmetry of the scattering, you're measuring size. So this is our first principle. The scattering is proportional to the mass of each molecule, the concentration, and this angular function that measures size. Okay. Now, we know that the molecules are diffusing around. This is one of the things that Einstein proved. Actually, he won his Nobel Prize for his descriptions of diffusion and Brownian motion. So imagine that I have light come from a laser and I have two molecules. And let's say I just get lucky, so that the distance from this one to the detector lines up to the distance from the laser to this one to the detector, so they end up in phase. Well, I'm going to get a bright signal. Now wait a little bit, and they diffuse around, and all of a sudden, now they're destructive. So if I have a fast detector, I will see it going fluctuating from bright to dark to bright to dark randomly. And the time scale for that depends on how quickly these things are diffusing around. If they're really big and they're diffusing slowly, then the time scale of it flickering between bright and dark will be slow. And if they're small, the time scale for them to fluctuate between bright and dark will be fast. So we use this mathematical trick. So this is sort of talking about, measure the intensity versus time. Here they're diffusing around. You can see it's going up and down slowly for a big particle and fast for a small particle. Well, we use this mathematical trick to measure the time scale. Obviously, your eye can see that this on the right is fluctuating quickly, and the one on the left is slowly. So there's a mathematical function called the autocorrelation function, which can quantify this. So I'm not going to go through the math, but basically that's what we measure. We measure this autocorrelation function to figure out how big the molecules are. And you can show that if there's something really big, it'll have a long time on this axis, and if you have something that's really slow, really big, it'll take a long time for it to switch between bright and dark. It'll show up as a curve that's delayed to the right. If it's fluctuating quickly, it'll curve to the left. So you measure the time scale on this graph, and you can measure how rapidly they're diffusing. And Einstein solved another problem, which is if I have a sphere and I ask, what is the diffusion constant of that sphere given Brownian motion? He came up with this relationship that relates the diffusion constant to the size. So we measure diffusion constant, we use his relationship and invert it to get the size out. Okay, so that's the basic physics. Let's talk about the chemistry. Chemists like coarse grade. So all the details of constructive, destructive interference and angular effects, this is what chemists think. Well, this is what they need. The intensity is giving you the mass. The angular variation gives you this measure of the distribution of mass within the molecule, this RG. The dynamic effect is giving you a different measure of how it diffuses, which gives you RH, and the mobility, electrophoretic mobility, how rapidly things move when you apply a field gives you the charge. And so now you can do some interesting science. When I joined Wyatt, this is what light scattering looked like. You put a sample in a little batch cuvette, little glass thing, into an instrument, and you get an average of all the different things around here. You got some big ones, some small ones, you get an average. The thing that really transformed this into a very important tool in biotechnology and biochemistry is once you can put it as part of a fractionation process. So if I have a mixture of molecules and I put them in a light scattering instrument, I just say, get an average. If I can combine it with some process where I can pull the molecules apart and look at the small ones and the mid-sized ones and then the big ones separately, then I can get a lot more information. And this whole industry evolved by connecting this to fractionation techniques. Now I'm gonna not go into that so much right now, but let me just talk about how that you do that magical process. So this is well known by chemists, but when I was, a physicist and joining Wyatt, it's like, chromatography, what is that? Okay, so here's size exclusion chromatography 101. And I argued that this is critical because applying light scattering with fractionation gives rise to an enormous number of applications you just couldn't get otherwise. So here's how you fractionate things. Take a bunch of porous beads. So if you want to make a chromatographer or a chemist really unhappy, refer to this process as just magic sand in a tube. So here's the magic sand. It's got these little pores. It's porous, and you put it inside a tube. And if I look at what happens to small, medium, and large molecules, the red ones are small. Well, the pores can get into the small ones can get deep into the pores. The intermediate sized ones can go a little ways down, but they can't get down into these little fingers. And the big ones are completely excluded. That's where the name size exclusion comes from. So if I fill a tube with this magic sand and I push the sample through, then what happens is they all start together because they're all mixed up. But the little ones, since they can diffuse in and out, they basically see more available volume. So they travel down more slowly. And the longer you wait, the more they separate out. So this is like when you have a coffee filter and you let it dry out, you see these little color bands. It's doing the same process. And the word chromatography actually came from the fact that when you use vegetable dyes, you can see the different colors. But you put a sample in one end, and what comes out the other end are just the big ones, then the mid-sized ones, and the small ones. So that's a way, taking a mixed sample, fractionating it into fractions, and then connect it to light scattering and other instruments as part of an analysis chain. So this is what that chain looks like. You take some solvent with some degassers and filters. You pump it through another filter to make certain it's clean. Reject the sample. It goes through a bunch of these columns, and then the different size fractions go through a light scattering instrument. And then you need to measure the concentration as well. So we use another instrument called the refractive index detector to measure the concentration. And there are many ways of measuring concentration. You can use, but this is what the prototypical system looks like. So what do you get? Let's say I take my Thanksgiving gravy. Thanksgiving gravy is mostly, collagen and the albumin that comes from cows. That's what makes gravy thick. So there's this reference standard which people love to use called bovine serum albumin, which is basically the plasma that comes out of cows. There's a similar one called human serum albumin. You can also get it. It's a little more expensive. BSA is super well characterized. You put it in. It's a protein. Like I said, the small ones come out first. Sorry, the big ones come out first because they see a smaller volume. Then the intermediate size and then the small ones. So here's a measure of the concentration of what was coming out of that column, going up and down. And with our light scattering, we can measure the molar mass. So this is the mass of just the individual molecules. And here's the mass of this one. It turns out on this axis, it's about 66.4 thousand Daltons or grams per mole. The dimers are exactly twice the size. The trimers are the 3 times and so on. So you can put in a mixture and get all the fractions out. And you can measure the mass of each one of these with light scattering and on them. Okay, so now we're getting to something that people might be interested in. One of the reasons light scattering is so valuable is because there are very few assumptions. It literally goes back to these fundamental understanding of the propagation of light. So we go from measurement of intensities to masses. We don't have any models that we're applying where the time that it takes to go through that column, some columns are, the samples go through faster or slower. It's a very non-invasive technique because most of the light, 99.999%, actually goes right through and doesn't interact with it at all, so you don't damage your sample. So non-invasive, quantitative, and it can be measured online as part of the fractionation. And the parameters that go into it are things that are easy to get at. We know the color of the light we use, we know the angles because we set them in the instrument, and certain phenomenological parameters that are easy to measure. Okay, so this is our flagship instrument. It is called the Dawn Neon. And somebody said they worked with Phil Wyatt early on, and their instrument was called the Dawn. And they've been recycling this name over and over again. So the instrument we sell now is called the Dawn. I think they just got really fond of the name. It's sort of like, the cars from the Mustang, for example. The Mustang today is nothing like the Mustang from 30 years ago, but they love, or 40 years ago. So they love the name. So this instrument has sort of the spirit of the old instrument. It's got this flow cell where the sample comes in, moves through this piece of glass, it comes out. There's the array of detectors that measures the scattering. We can control we measure at different angles. We can control the temperature over a wide range. And we can measure things from about 100 Daltons. That's 100 grams per mole. That's something that's salt, not much bigger than a salt, up to 100 million. And that means a mole of this would weigh 100 grams, and a mole of this would weigh 100 kilograms, 100,000 grams. We can measure things from 1 nanometer to half a micron, about the size, the wavelength of light that we can measure. And as an absolute technique, it's pretty good. We can measure absolute weights to 2 to 5%. Reproducibility is much higher. We can do much better than 1%. But think about it, it's very non-invasive. You can measure with salts. You can measure aggregates. You can measure things that are very weakly bound together. Now, the one last fractionation technique I'm going to talk about is an instrument that we just released 2.5 years ago, but it's a technology that goes back quite a bit longer. It's called field flow fractionation. Size exclusion chromatography is great for fractionating molecules. This is great for fractionating particles. In particular, things like COVID vaccines. They're big. They're 200 to 300 nanometers. And I'm going to talk about that as one of the applications. So field flow fractionation is an alternative fractionation technique that works well for molecules. And it's a really fascinating idea. It is, okay, let's say I have a membrane on the bottom of a flat plate, 2 flat plates, and I apply a flow through the membrane so that the solvent can go through, but the sample cannot. The sample will start loading up onto this membrane. This is supposed to show. And it'll start concentrating onto that membrane. And whenever you have a big concentration, there's a diffusion will try to remove that concentration. So you get a force pushing them down and diffusion that's going to try to raise them up. And if you consider something big, they get pushed down really hard and diffusion is small. So on average, they sit close to the membrane. And now if you think of a small molecule, the force pushing them down is small and the diffusion is big. So they're still going to stack up near the membrane, but on average, they're going to be higher up in the channel. The big ones are near the wall and the small ones sit up higher. And then you apply another flow from the end and there's a shear. So something that sits up higher in the channel will move downstream more rapidly. So in this fractionation, the small ones, which are on average higher up in the channel, will come out first. And the big ones. Okay. Here's a little simulation of what that looks like. You inject the sample, you push it down against the membrane, this step called focusing. And so now first it was filled floor to ceiling, but then they all sort of accumulate down here. The blue ones are the small ones. And then you switch some valves so that all of a sudden the sample started to push down the channel. And will end up being separated out from the big ones. And the nice thing about this is by adjusting the flows through the membrane and across the channel, you can tune it to small molecules up to big particles. Okay. Now, I would be remiss by not talking about the product that we just released this year, and that's one that measures charge by measuring the Doppler shift that you apply, that results when you apply an electric field. So this is an instrument where we use a laser again, and we do scattering, and we interfere the scattering with light that went around the cell, but by using this fiber device. And the net result is when you apply a small electric field, these things move at about 1 micron per second. And with the scattering, we can measure changes in the velocity of these particles to that level, or actually better. And so you can measure the electric field points up and they move up, it's down and it moves down. So you can measure how much charge are in these things. Okay, so let's put this all together, talk about some applications. First application, probably the very first thing people did with light scattering is they characterized polymers. And this really came out of World War II, where there was this big run on natural polymers like latex, and there was a huge industrial buildup of how to make synthetic polymers, synthetic rubbers. And they had absolutely no way of knowing what it is that they generate. So light scattering became one of the go-to tools for characterizing polymers that are long rods, long, are coiled up into chains, are they branched, do they have arms, like this is called a comb, or they have a bunch of tendrils, like it's called the dendrimer. And the net result is you can shine light scattering on these and figure out, well, how many short ones and how many long ones do you have? How many branches do you have? Is it comb shaped? Is it star shaped? And this affects a lot of things, like how strong they are, whether or not they make good adhesives, whether or not they break or brittle. And what you can get from this is you can measure basically the length distribution, the size distribution of these things. But I'm going to skip to the more interesting one. Let's talk about a biological application. So here's one that I would argue that the polymer applications are valuable, but where we've seen biggest growth is in pharmaceuticals and vaccine development. So here's a case study of one of our customers that makes insulin. Now, the way they make insulin these days is they have recombinant bacteria that have been genetically engineered to basically be little insulin factories. And they make big reactors of them. They grow these E. coli bacteria that have been engineered to produce insulin. And at the end of the growth, they have to purify the insulin and get rid of all the bacteria. And when they do that, one of the things that can go wrong is sometimes the insulin molecules will stick together. And or you can put it on, they have a good sample, you put it on the shelf, and you let it sit. After a while, the molecules will start to aggregate. If the aggregate's too big, all sorts of bad things can happen. I'm a physicist, but my friends that are biologists tell me this is not a good thing. Basically, you start plugging capillaries, or worse, your body will have an immune reaction, basically saying, okay, these big aggregates are on a foreign body, and let's try to get rid of them. Clearly, if you're taking this, you can't have an immune reaction to insulin, or you would very quickly no longer be able to take it. Okay, so there's a requirement that you have to characterize how much of these samples are in different aggregation states before they're safe to use. How can we do that? I just showed you an example with BSA of how you can measure how much is in the monomer state when molecules are fusing around by themselves, how much is in a dimer state when you're stuck together. So here you can do the same type of measurement. You can measure the molar mass. Here's the monomer of this material. And you can say, okay, 85% of this sample, this is the total mass that has that weight. 85% of that sample is in the monomer, about 15% of the sample is the dimer, and about 5% is in higher order states. So here's a very simple example of how you can use light scattering and the fractionation in order to figure out from the sample how much is in each aggregation state. And so this would probably be a reject. Okay. So let's talk about something more topical. In the last few years, we've seen huge growth. When COVID came out, there was this huge rush to try to understand how to make a vaccine. And this technology of using lipid nanoparticles had been around for a long time, but it's a challenging technology to tame because these are very complicated assemblies. So these lipid nanoparticles, just give you a quick background of what they are. They consist of a small genetic payload. And for the ones for the COVID vaccines, it's an mRNA molecule. There was a lot of work to make them stable because mRNA is a very fragile molecule. And if you don't protect them, they just fall apart. So the way they protect it is they put it in these little tiny fat droplets called lipid nanoparticles that are made of basically fats. And so there's also things you can do to these fats to basically stabilize them, but they become the capsule that holds the RNA payload. I like to think of this as like, those Easter eggs where you put candy inside or not, and you make these things that are empty, or you can make them load them up, put the candy in and close them. But that's essentially what these things are. But now you make them, there's a bunch of things. Why are they good payloads for vaccines? Because they're fairly easy to make. Once you have a technology, you can make large amounts of these things because the lipids are pretty easy to control. But by encapsulating them, you can protect the payload from being damaged. Recently, figuring out, okay, how big are these? How much payload are you putting them into? And how to modify them to have them target specific cell types. Because this technology has been very successful as a vaccine, but very quickly it's going to be used for things like cancer therapies, where you can make a vaccine that is specific to one person's cancer. So you can take the DNA, figure out, okay, if you have an immune response to that particular cancer cell, then you can make a personalized cancer vaccine. But you then have to target it to a specific cell type. So there's a lot of work to do that. And you can put a lot in or little, depending on how big these things are. It's a very flexible vehicle. How do you characterize them? They're easy to make. It's hard to make them all exactly the same size. They can vary up to 50 to maybe 200 nanometers. These are well beyond what you can do with size exclusion chromatography, but it works great with field flow fractionation, is why I had that digression. They're mostly spherical, and how much payload you get depends on details of how big they are, how good the encapsulation process is. So this is the prototypical system for characterizing lipid nanoparticles that we've been pushing at White Technology, where we're going to use that field flow fractionation fractionator to fractionate them out. So you take this polydispersed sample, and then you take all the fractions out. You bring them into a UV detector to measure basically how much of the genetic material is in it. It goes into the light scattering detector, and then it goes to refractive index detector. Between these three detectors, you can figure out how big the molecule, the assemblies are, and how much is inside them. Okay, so here's one example from one of our customers. So here, they made lipid nanoparticles, and they made them at different concentrations. And they wanted to make certain that the RNA inside them wasn't doing something bad, like the big ones to the aggregate. And so you make big concentrations, small concentrations, and the payload RNA is basically unchanged. So you can demonstrate that the RNA is actually not being affected by floating. You could look at empty versus full. So here's a bunch of empty ones, and you can measure their size. Light scattering, you get size, and then you can look at loaded ones and say, sure enough, the loaded ones cause them to swell a little bit. You can look at the distribution of sizes. And here's the two different popular vaccine vendors, Pfizer, BioNTech, and Moderna. And you can see that they have very different control of their process. They're doing something that's very similar. They're not exactly the same. I, for example, always got the Moderna ones because they were the first, and we've been working with them for years. But in fact, BioNTech appears to have better control over the average size than Moderna does. Moderna has better control of the stability of the RNA. Both of them have shown to be safe, but if it were up to me, I'd probably use the Pfizer vaccines in the future. You could look at how they change over storage. So here's two that have been sitting in storage for a while, and you can see this batch, these two after storage, did not change their average sizes. These two batches did. So you can use something like this to determine basically how they're aging. Remember I said you can get two different size metrics. You can get a measure of the distribution of mass, and you can get a measure of how much they diffuse. If you compare the two, then you can ask whether or not things are round or not. And so here's an example. There's a metric of the ratio of these two different sizes, the ones you get from the angular symmetry of the scattering, the ones you get from the diffusion. And this ratio says they're essentially perfectly spherical. And then the last thing is probably the most important one, is how much payload are you putting in each one? When you have these three detectors, you can measure the mass of the lipid portion, you can measure the mass of the RNA payload, and you can look at the loading capacity. Basically, of the weight, how much is the payload, how much is the cavity shell. In this case, this was about 12% payload, and the rest of it is the shell. Okay, so hopefully I motivated why pharmaceutical and chemical companies care about the sky is blue. Is you can measure the weights of molecules, the weights of complex assemblies. You can measure their size. You can measure, how much they're loaded. There's other parameters you can get about how they interact with each other. Do they want to stick? Do they want to repel? And the range of applications is astonishing. When my parents asked me once what I did for a living, I said, well, we weigh things by shining light on them. Is there a business in that? I said, yeah. I said, okay. They knew that I was passionate about it, but the applications are astonishing. Vaccines, protein folding, people doing crystallography, people looking at materials, how to make plastics hard, how to make food starches that degrade. Actually, a lot of this idea of how to make degradable plastics now, by putting in linkers that will come apart. You can use this for measuring it. The field flow fractionation, you can take samples from the environment. You can fractionate out and say how much is biological material, how much is synthetic material. The range of applications is just astonishing. Phil Wyatt had this great phrase. He said, the words are different, but the music is the same. So you get polymer chemists and biochemists talking to each other, and they're really talking past each other, but they're really using the exact same concepts. So hopefully I've motivated why people care about why the sky is blue. And here's a beautiful view from Santa Cruz Island. And maybe here's another way of doing light scattering. So thank you very much. Have a question.
If people have questions, you can, if you're on the Zoom, you can unmute yourself and ask the question, or you can type in the chat, whatever you're comfortable.
I know you're all physicists and you got all the physics, right?
Can you tell us anything about your current instrument that you're working on?
Yes, but I would probably get fired if I did that. I will say that one of the things about, okay, I've been with White for 27 years and now it's Waters. And Waters is a big company. They do a lot of other things. They make mass spectrometers, they make the chromatography columns, they make the pump systems. There's a lot of integrating our technology with the traditional Waters technology. So I would not be at all surprised if there's strong light scattering with mass spectrometers, which also measure the mass of molecules.
Right.
Light scattering is beautiful in that you can measure with salt. You can measure weak aggregates. These lipid nanoparticles, you put them in a mass spec, and a lot of times they just blow apart. It's very hard. Light scattering has the ability to measure in different complex solvents. Mass spec can only have very purified candy salt, for example. Biological samples, bodies are filled with salt. Keeps our proteins from aggregating. So there's a lot of stuff there. The field flow fractionation is growing very rapidly. So there's a lot of innovation that we're working on that as well. In my time at Wyatt, one of the good things is that we had way more ideas than we could possibly carry off with a company the size that we were. And my hope is that with the resources of a bigger company, we can do more. Whenever this company acquires another one, it takes a long time to just sort of work out the logistics and so there's a bit of chaos of you have to train the water staff on how our instruments work and what applications they can use for and service support. But my serious hope is that we will broaden the number of things that have been sitting around, good ideas that we just couldn't do before.
You went really fast, but you said between Pfizer and Moderna, one of them seemed to have better control over the process.
Well, I would say that it's not clear which one is a better product. I will say that the testing for safety and efficacy is the gold standard. They both work. They're both safe. They're both efficient. The question is, who has tighter control of the process? Well, one has a very broad size distribution. The other one has a fairly narrow size distribution. Is that important? I'm not a biochemist, so I can't say. But I know when I build instruments, and I've been building, built most of the instruments that Wyatt sold, control over the intermediate steps is critical to having control over the entire system. So I like things that are tighter size distribution. Now, maybe there's a biological reason why wider size distribution is better. I don't know. But
Which one had better control?
the Pfizer.
Pfizer.
Pfizer did, yeah. All right. Well, we don't know what that means exactly, but that's.
Yeah. The funny thing is, we had been working with both these groups for many years, and nobody had ever heard of BioNTech or Moderna. They were small companies that had been working on this technology for like, 10 or 12 years. And the remarkable thing, it was the right technology, the right time, the right problem, which is how we ended up with a vaccine in a year. Which in the vaccine business is that's just it never happens.
Unheard of, right?
Unheard of. And here's a little idiosyncratic view from my part. Pharmaceutical companies were mostly interested in medicines. Vaccines was a little bit of a backwater because most of the infectious diseases don't affect the third world. And there was a lot of research for trying to help the developing world for malaria and all these other diseases, but it wasn't a huge resource investment. And now it is, right? And this technology, like I said, it's super flexible. So you could easily imagine these things being used for cancer or other infectious diseases. Alzheimer's, there are people who are working on doing that. There's a lot. It's a very rapidly growing field because this technology is very flexible. And we can help third parties.
Can you talk a little bit more about the shell, the LNP?
Yeah.
For vaccines, whether they're the same for or very, very similar for Pfizer and Moderna and vaccines, and whether they differ for other medications?
So I don't know anything about other medications. I will say that the reason that there were two fundamental problems, the way these things was a great assault because I'm a physicist and not a biochemist.
So
The way these things work-
right, neither am I.
So I learned in my biology class 40 years ago that DNA is a repository of information.
Mhm.
It gets transcribed by mRNA, which is
Yes.
basically like Post-it notes that go into the giant book of life.
Yes.
And you copy a section, and that Post-it note goes to the factory, which is the ribosome. And the ribosome reads that, the mRNA takes that, and the mRNA is read and converts into amino acids to make proteins.
Mhm.
The mRNA is destroyed. So it is a Post-it note that only lives during that process.
Mhm.
And the way these vaccines work is we don't touch the DNA. Okay. We
Right.
basically put a bunch of Post-it notes into the cells saying, make these proteins.
Right.
And these proteins are the spike proteins on the surface of the COVID.
Right.
And then your body creates these spike proteins, and your immune system says, hey, all these spike proteins, let's make an immune reaction, and it primes your immune system. And then it's your immune system that has the memory of how they make them. But the mRNA that was in your cell is long gone. It only lasts about a day.
Right.
And there was no modification of DNA, so it doesn't know how to make it anymore.
But the LNP.
Yeah.
That shell, okay, that's what I'm curious about. Is that shell the same kind of, you're going to be using a shell, in this case for the mRNA. But for
Yeah.
drug delivery,
Ah,
how is it gonna, it's gonna vary, it seems to me.
so
So,
The-
what do
the-
you know about it?
okay, first off, things like cholesterol particles are very similar in structure because they're lipids. The actual shells that they use for delivering other drugs, I know there are people working on this technology. The big thing that they're working on is how to target it, how to basically put a
Yes.
protein on the surface saying, okay, you go to the liver.
Yeah.
Okay. And then also there are some body tissues that are attracted to things that are highly charged, and there's other body tissues that are attracted to things that are only weakly charged. So the instrument I talked about that measures electrophoretic mobility can measure the charge of the assembly. It can also measure the charge of the individual lipids that go into it. So there are people who are controlling the charge on these things to help target them, and they're putting in markers on the surface to help target them. Now, I don't know if these are the same shells that they use for like cancer treatments. I don't think so.
Yeah.
Again, I'm out of my depth.
You've done a wonderful job, Steve, I think, of starting from the beginning and going through how these instruments work.
Thank you.
So thank you very much for that.
I get a little bit into the weeds, my wife tells me.
Question, Steve. So you mentioned some pharma applications. Are there pure non-pharma, non-biological, chemical
For
applications?
LMPs?
No, for your water.
Yeah, so I in the interest of time, I blitzed through all the polymer stuff.
Mhm.
There's a huge range of applications. I am astonished when I read the papers of people use these instruments for things that I didn't know anything about. And to me, that's a sign of a successful technology. In some sense, it's a scale. You can measure gold, you can measure feathers. I mean, you can measure anything with it. So yeah, there's a lot of applications in our website. We keep a database of papers where people have published using our instruments. And I think we're up to 20,000 peer-reviewed papers. And so I go through that list and there's all sorts of things that it's like, I have no idea what they're using instruments for. And it's good because, I know how they work. And I'm critical in, I've been designing the products since I got there. And some of the products I designed when I joined Wyatt are now in our museum. No, but it's good because it means of those ideas, we had enough on how to make it more reliable, make it more sensitive, make it easier to use, make it more robust. And my analogy is, if you look, I do a lot of photography. In the early days of photography, Ansel Adams would smear emulsion around with fingers. He'd take his camera apart and move elements around, polish his own lenses. Nowadays, that's all highly, integrated technology. When I joined Wyatt, it was very much in the Ansel Adams days. They were all very different. It was a science, but there was more art than science. And now we're more science than art. And a lot of that is good understanding of the fundamental physics of how the process works. A lot of that is just old-fashioned engineering and hard work. And we have a really talented group of engineers. And for what reasons, I don't know if this is a model for the rest of the industry. Phil Wyatt, being a physicist, he had a very inflated view of the skills of physicists. So almost all of our product managers were physicists. And what I would argue is, got my PhD at UCSB in experimental physics. There I had to do my own electronics. I had to do my own machining in the machine shops. I had to do my own optics and computer modeling and so on. Now we have specialists.
Yeah.
We have mechanical engineers. We have electrical engineers. We have software engineers. I'm not the best mechanical engineer in the world. I'm not the best software engineer in the world, but I can talk to these people. And when I'm working on a project, I can pull them all together. Because a good electrical engineer often doesn't talk to the mechanical engineers with the same language. And so we're more the glue and problem solving. That's what physics education teaches you is to have a view of how to solve difficult problems.
I was looking at some of your papers, and there are several of the recent ones were about the measurement of flowing streams. And I was wondering what the applications of that are.
Flowing natural streams or streams of fluid?
Viscosity?
Measure viscosity or?
Perhaps I misunderstood you.
No, there's, like I said, there's 20,000 papers in our database. On our webpage, you can pick up a paper that I will have absolutely no knowledge of. And that's good because, and here's another really interesting thing I would argue secret sauce will get made by a successful company. Is that every time someone bought an instrument in the United States, we bring them to Santa Barbara for a 3 or 4 day training seminar. And we get people out of their offices so they can focus, because getting free time to focus on anything is just it's a rare commodity these days. But I would interact with people. Some were just novices and they were learning how to use the instruments, but some were world experts in their field, like the Nobel Prize winning labs. And they would tell me about how they use ours instrument and many others. We're not the only ones. But the range of applications literally is mind-boggling. My mind is boggling.
Questions from the Zoom? Anyone? Stephen, you have your hand raised.
Yeah, I've got my hand up. Yeah, hi, very great talk on this. I always considered Wyatt kind of a detector company. I don't know if you'd argue with that, but I don't. But now, as part of waters, it's going to be more of a system approach, in that they have everything. They've got pumps, and I think they have columns and all that stuff for chromatography as well, and mass spec and all those things. I was wondering, from a system integration thing, is this going to be an issue, or is it going to be a big open opportunity? Because now, instead of being a detector that worked with everybody else's pumps and sample stuff, now you're going to be part of a company that sells all that. Maybe the alternative is that you have software that integrates it all and makes it much easier to use, or do you lose some customers because you're going to push towards the waters version?
That is a very astute question. I will say that when I joined Hawaii, we were a detector company, absolutely. And we used to say we were the Switzerland of fractionation, because you want to connect to a thermo, you connect to Shimadzu, Waters, Agilent, we'd connect to all of them. Because at the end of the day, once the fractionation has occurred, we get a fluid stream and a capillary of the sample we characterize. And then we would have this cascade of our analysis chain of multiple instruments. And there's more I haven't talked about. People don't want necessarily individual components. They want to solve problems. So we have, in the last 10 years or so, really been pushing to solve, like the LNP problem. And that requires pumps, autosamplers, injectors, degassers, UV detectors. And so we've been going towards systems for the analysis anyways. And they'll get more tightly integrated into the waters ecosystem. I would certainly hope that we will not lose contact with the other vendors and other instruments. I don't think it'll happen anytime soon, because we have a large number of users, people who are doing good science using Agilent or using Shimadzu, and we're not going to turn our backs on them. I think in the future we will make more highly integrated systems that try to leverage the waters ecosystem. And if we integrate with mass spec, we're going to use their mass spec, of course.
Yeah, thanks. Yeah, good luck with sounds like a bright future.
Right now I'm still just waiting for the dust to settle, and integration is always a challenge. I will say that most of the activity has been, we have to train all of these. Maybe I shouldn't say this, but I'll say that.
Second thought.
I looked at the company, and very analytical. So I looked at, how quickly we build instruments. And I said, look, we have really good technology. We don't have the sales and distribution network to really capitalize. And the last thing the marketing and sales people wanted to hear is from the technical staff is, what we really need to improve is marketing and sales. But Waters absolutely believes that. So they have a huge distribution network. And so the number of people who will know the technology, who can talk to users and figure out how our technology can solve their problems, it's growing dramatically. So I expect that the number of applications will grow, and the number of people who know about the technology will also grow. Because for the longest time, every talk was, what is light scattering and what can it do for me? And I give you a little bit of it here. But it's now to the point with this large number of applications that papers don't start off explaining the science anymore. They say it's an accepted technique and this is what we did with it. And that evolution is continuing. And I think that will continue further, because the chemists, they don't want to know all the details of how it works, because they have difficult problems. They just want to know that it does work, or if it doesn't, why not?
Okay, thanks.
Any other questions from the Zoom? Room? Well, thanks very much.